Every energy transfer or transformation increases the disorder of the universe. Simply said is when you get 100% solar light energy, when the sun emits 100% solar energy, only a portion of the energy is absorbed by the chemical energy. The rest will be lost as usually as heat, and this is what we call entropy or disorder. Entropy is a measure of randomness or disorder within a system. More energy lost to the surrounding means that it is less ordered and it is more random the system is. Simply said that high entropy equals to high disorder equals to low energy. So from a solid form, when it changes into a liquid form, it will increase its entropy or disorder. Okay, in terms of energy, it is let's begin. For the energy to occur or to happen, it can be divided into it either being spontaneous or not. So according to the Gibbs free energy, spontaneous processes occur without energy input. They can happen quickly or slowly. For a process to occur without energy input, it must increase the entropy of the universe. This reaction can be determined by calculating the free energy, which usually represented by the G. Free energy, called Gibbs, refers to energy associated with chemical reaction that is available after entropy is accounted for. But how about non-spontaneous processes? Free energy is a measure of a system's instability, its tendency to change to a more stable state. Equilibrium is a state of maximum stability. During a spontaneous change, free energy decreases and the stability of a system increases. A process is spontaneous and can perform work only when it is moving toward equilibrium. Equilibrium can be stated as A plus B interchangeable to C plus D. If we focus on the figure here, on the diver and the solid molecules and the chemical substrate here, we can see that we know that all three of these has more free energy, higher G, and it is less stable but has greater work capacity. When the diver dives or the molecule disperses and the chemical reaction happens, it is in a spontaneous change where the free energy of the system decreases, G is less than 0, the system becomes more stable, and the released free energy can be harnessed to do work. And finally, when the diver dives, the molecules diffuse and the chemical reaction happens, there are less free energy, it is more stable and has less work capacity. the free energy change is, or the standard free energy change, is the energy change occurring when a reaction under standard conditions proceeds from start to equilibrium. The change in free energy during a process is related to the change in enthalpy, or change in total energy, change in entropy, and temperature in Kelvin. So, to obtain the free energy change, it is when the total energy minus entropy, total entropy, change in entropy, and includes the Kelvin as temperature. Only processes with a negative standard free energy are spontaneous. Therefore, if the standard free energy is equals to 0, it is at equilibrium. There are no release or requirement of energy. Reaction is at equilibrium. When the standard free energy is less than 0, the reaction releases energy as it approaches equilibrium. It does not use energy but releases it, and reaction proceeds forward. As for standard free energy more than 0 or positive, the reaction requires that energy be added to proceed in the direction indicated, meaning to say that it uses energy for the reaction to occur. And the reaction here proceeds in reverse. Okay, so let's do a little bit of practice here. Maybe it's a little bit cut down here, but it's the location of a bowl. Okay, I've reduced the size of the figure here. Okay, so from 1 to 5 is the movement of ball. The ball will start at number 1. So choose which position is spontaneous, non-spontaneous, and at equilibrium, and why. Okay, so when the ball is at the number 1 position, it has the highest potential energy. So it doesn't need any energy or just a little bit of activation energy for the ball to drop and go into the U form. In the 5th position, the ball is using the kinetic energy from the potential energy from the 1st position to reach the 5th position. And for the ball to reach 3, the 3rd position, is when neither energy is used or released. Therefore, position 1 is the spontaneous position because it hardly needs any energy for it to suddenly move. And when it falls into the U form, when it reaches the 5th energy, it is the non-spontaneous position because it needs energy for it to move from the potential energy here. Once it started moving, it started releasing using kinetic energy. And when the kinetic energy finishes and reaches the 3rd position, it is in equilibrium, meaning to say that it doesn't need any energy for it to maintain here, or nor it releases any energy. spontaneous, non-spontaneous, and equilibrium. In biochemistry, the free energy change is usually measured at 25 degrees Celsius, 1 atmospheric pressure for a gas, which is 100 kilopascals, and at a concentration of 1 mole for solutes, except for hydronium ion, which is at pH 7. These conditions specify a standard energy change, which is represented as standard free energy change. So the equilibrium is A plus B interchangeable to C plus D. And the K equation is C times D over A times B. The standard free energy change can be related to the equilibrium expression, which is standard free energy change equals to negative gas constant, which is at 8.316 joule per mole, and temperature, which is Kelvin, which we use at, if it's stated in room temperature, it is in 298 Kelvin. And then natural log, which you can easily find in a calculator, or usually known as ln, and then the K equation, which is the equilibrium constant. So let's go into practice 3. Determine the standard free energy change for the isomerization of glucose 6-phosphate to fructose 6-phosphate. To start, solutions are mixed that result in an initial concentration of 1 molar for each species at standard conditions. So, if it's stated at standard condition, we're going to use this equation. So, at equilibrium, glucose 6-phosphate has 1.33 mole, and for fructose 6-phosphate, it has 0.67 mole. So how do we calculate this? By using this equation. We simply use this equation or this calculation. So the standard free energy change equals to negative R, which is gas constant at 0.316 joule per mole, and then times T, which is the temperature in Kelvin, which is 298 Kelvin, and then natural log or ln 0.5. 0.5 is obtained through the K equation, where the fructose 6-phosphate is divided by the glucose 6-phosphate. The product is divided by the initial product, and will obtain 0.5. And finally, the answer will be positive 1718 joule per mole, or we convert it into the standard unit, kilojoule per mole.